Hey friends, welcome. We'll take a look at some of these review problems that we had for our Unit 2 test. This is just the back side of the first page of the test, the one that we're offering for a retake. And so here's some extra practice that is meant to help you along. We're going to try some of these in a couple chunks. I'm going to do a video of 1 and 2, a video of 3 and 4, a video of 5, 6, and 7. So maybe you can watch the one that you most need, or maybe you just want to check all your work. I'm also going to do this in a couple different ways just to help you out with the understanding. So, number 1, a car begins its drive in heavy traffic and continues on the highway without traffic. The average cost in dollars of the gas this car uses per mile for driving a certain number of miles X is given by this equation. So I see that I have kind of a set cost here and a cost per mile that I see, and we're taking that total and dividing it by the number of miles we're driving. As x gets larger and larger, what does the end behavior of the function tell you about the situation? We can look at this in a couple different ways, and this one I want to look at in 2 different ways to show it. If we're looking for end behavior, and we're looking at some kind of a graph that we have here, we have seen a lot of our rational functions have some asymptotes, and so I start first by thinking about where those asymptotes are happening. When we have 2 parts to it, right? We have a fraction and we're adding or subtracting something to it. This denominator tells us our vertical asymptote because it tells us what number x can't be equal to. That's what's going to tell us our vertical asymptote. It is the constant that is not part of the fraction that would tell us the horizontal asymptote. So one of the ways that I could look at this problem is to force it into vertical asymptotes and horizontal asymptotes. And this means I need to somehow have it where I've got a constant that is not part of the fraction, which I have now. Everything's in the fraction. So I want to write each of these 2 terms as 2 separate fractions. They're separated by addition. And so if I write both of these as 2 separate fractions over x, I would have 0.65 in the first fraction and 0.15 in the second fraction. But there's an x that comes after that 0.15. So I'm just writing this as if I didn't add them together already with a common denominator. I'm kind of ripping them back apart into 2 separate fractions. And now I should see that I have a time where I'm multiplying by x and then dividing by x. So these ones will cancel out. And what I have left is 0.65 over x plus 0.15. If I can write it in this way, my vertical asymptote and my horizontal asymptote get a lot more clear. But I also see I have something that's a fixed cost and something that is happening per mile, this 15 cents that seems to be a charge per mile. So I see that much better here when I write it in this form. I have a vertical asymptote where x cannot equal 0. Can't have a denominator equaling 0. So I'm going to have a vertical asymptote right on the y-axis. And I'll have a horizontal asymptote here at 0.15. And so our graph will look something like this. I know, though, it doesn't make sense to have negative miles that this car is driving. It's not like I'm going to make money by driving negative miles or something like that. So this part doesn't make much sense, but this part definitely does. And so this end behavior tells me that as I drive more and more miles, it's talking about x moving in this direction, as I drive more and more miles, the cost is going to get closer and closer to 15 cents per mile, but it's never going to quite touch it. I'm always going to have this 65-cent charge, I guess, that is going to also need to be divided per mile. So that's how I'd answer that question. As x gets larger and larger, the more miles we drive, the closer the cost gets to 15 cents per mile. That's how we would interpret what that asymptote means. The more and more miles we drive, the closer and closer that graph is getting to our asymptote at 0.15. If you have a graphing calculator and you're using it, we could also type the original equation into our y equals, and we could just see what is happening with this graph. So in parentheses, 0.65 plus 0.15x, close those parentheses, and divide the whole thing by x. And when I look at the graph, I see that shape that I just drew on my paper. But we're not going to see it until we get to larger and larger values of x, what it is we're looking for. So if I look at my table of values, maybe that's a good place for me to look at. First of all, I see that error happening at 0 that I was expecting. Let's see if I can get this to be a little more clear for you. So I see that error happening at 0. And as I go farther and farther to bigger and bigger x's, I see this number going down, 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 down. It's getting to a small decimal. It's getting smaller and smaller. But if I go to some really giant, big value of x, it might show me something really interesting that's going on, because I don't know exactly how far down this is going to go, or how much longer I have to get before it might go to 0.14. So instead, if I go look for an x value of something like, I'm going to change my table setting so I start at some really giant number like 10,000 and see what that looks like. Now it becomes really clear. See how it just is the same number over and over again? I see that it's getting closer and closer to 0.015, and it'll never quite get there. Our big thing, though, is the interpretation going on here. Number 2 asks us to write a rational equation. Ratio means I need to have a fraction. Equation means it has to equal something that cannot have a solution at x equals 2. That's where I want my an x value that can't happen. And again, I'm going to return back to this idea that I have a fraction and the denominator cannot equal 0. There's my x value happening. So I cannot have some denominator where I have x minus 2 in the denominator. This is one of the simplest ones I could write, because if I plugged in 2 for x, my denominator would end up with 0. Now, it really doesn't matter much of what else I put here. So maybe I have something like 14, and maybe something like 10. The important thing, though, is that we want to set it up so my denominator can't equal 0, and that means that my x cannot equal 2. Cannot have a solution at that point. Alright, that's my first video. Feel free to watch the next ones coming up on the rest of this handout.